You have lived inside gravity for so long that it no longer feels like something you are experiencing, but rather something that simply is. A quiet background condition that shapes every movement without ever asking for your attention. Every step you take, every object you release, every moment your body rests against a surface follows the same pattern. And through repetition, that pattern has turned into something that feels self-explanatory rather than something that invites curiosity. There is a particular kind of certainty that comes from familiarity, the kind that does not arise from deep understanding but from constant exposure. And gravity fits perfectly into that category. You do not question why things move the way they do any more than you question why the sky stays above you, because both appear to belong to the structure of reality itself, fixed and unquestionable. The moment you let something slip from your hand, your mind does not pause to interpret the event. It recognizes it instantly, assigns it a cause, and moves on, carrying with it the quiet belief that nothing important remains to be explained. That belief rests on an idea so deeply embedded that it rarely surfaces into awareness, which is the assumption that direction itself is built into the world. The notion of down feels as though it exists independently of you, as if space were organized with an inherent orientation that everything must follow. Yet that sense of direction is not universal. It is anchored entirely to your position on the surface of a massive object. And if that context were removed, if you were placed far from any planet or star, the distinction between up and down would not fade gradually but disappear altogether, leaving behind a space with no preferred direction at all. What seemed like a fundamental feature of reality reveals itself as something local, something dependent on circumstance. And once that realization settles in, even slightly, the explanation that once felt complete begins to loosen. Saying that objects move downward no longer sounds like a final answer, but like a description tied to a specific environment, one that does not extend as far as it first appeared to. At that point, the idea of a force enters almost automatically, offering a way to restore clarity by giving motion a cause. An invisible pull acting between masses, reaching across space and guiding objects along predictable paths. It is an idea that has proven extraordinarily successful. And because of that success, it carries an authority that is rarely questioned. Yet the word itself does a subtle kind of work, replacing curiosity with confidence, creating the sense that something has been explained, when in reality it has only been named. There is another way to look at the same situation, one that begins not with attraction but with what you can feel directly. As you sit or stand, your body experiences a constant pressure, a steady sensation that you interpret as weight, as though something were pulling you downward. But that sensation does not arise from motion itself. It comes from resistance, from the surface beneath you, preventing a movement that would otherwise occur. The ground is not merely supporting you, it is continuously interrupting a motion that you do not usually notice because it never has the chance to unfold. If that interruption were removed, the change would be immediate and unmistakable. The familiar pressure would vanish. Your body would no longer feel anchored. And what you would experience is often described as weightlessness. Even though nothing about the underlying gravitational influence has been turned off, the difference lies not in the presence or absence of gravity, but in whether anything stands in the way of motion. This is the detail that does not fit neatly into the simple picture. The sensation most closely associated with gravity turns out to depend on constraint rather than attraction, on being prevented from moving rather than being pulled. The more closely you examine it, the more the familiar explanation begins to feel incomplete. Not because it fails to describe what happened, but because it leaves something essential unaddressed. Nothing in the visible behavior of the world has changed. The paths objects take remain exactly as they were, and every observation still aligns with what you have always seen. What has shifted is the meaning you assign to those observations. The quiet recognition that the explanation you trusted may only describe the surface of a deeper structure. The simplicity that once felt satisfying begins to give way. Not dramatically, but gradually, as though it were making room for a different way of seeing that has not yet fully taken shape. Long before the idea of gravity became something you could write down as a precise rule, the world was divided in a way that now feels almost impossible to accept. Yet for centuries it seemed completely natural. What happened here on Earth, where things fell, broke, and changed, was believed to belong to a different category of reality than what happened in the sky, where planets moved with an elegance that appeared untouched by the imperfections of the ground beneath your feet. These were not just different behaviors. They were thought to follow entirely different principles, as if the universe itself had drawn a boundary between the ordinary and the celestial. Into that divided picture stepped Isaac Newton, and what he proposed was not merely a new idea, but a collapse of that boundary so complete that it reshaped how reality itself was understood. Instead of treating the motion of an apple and the motion of the moon as unrelated phenomena, he placed them within the same framework, suggesting that the very same influence responsible for the fall of objects near you also governs the motion of bodies far beyond your reach. This was not a metaphor or a loose analogy, but a precise claim that a single principle operates everywhere, from the smallest scale you can observe directly to the vast distances of the heavens. To see what makes this so powerful, you have to shift how you imagine motion in the sky. The moon, which appears to hang above the earth in a steady, predictable path, can be understood not as something supported or suspended, but as something in continuous motion toward the earth, always falling, yet never arriving. That idea sounds strange at first, because falling usually implies an end point. But here the motion sideways is just as important as the motion inward, creating a balance in which the earth curves away beneath the moon as it moves, so that the fall never completes. The orbit is not a special kind of motion separate from falling, but an extension of it. From this insight emerges a rule that is both simple and astonishingly far-reaching, stating that every object with mass attracts every other object with a strength that depends on how massive they are and how far apart they remain. The larger the masses involved, the stronger the interaction becomes, while increasing distance weakens it in a precise way that can be expressed mathematically. What makes this rule extraordinary is not only its simplicity, but its universality, because it does not distinguish between objects based on where they are or what they are made of, applying equally to stones, oceans, planets, and stars. With that single idea, the universe becomes something that can be predicted with remarkable accuracy. The paths of planets can be calculated, the return of comets anticipated, the behavior of tides understood as the result of gravitational interactions extending across vast distances. Even objects that have not yet been observed can be inferred from their influence on others, allowing new worlds to be discovered not by direct sight, but through the careful analysis of motion. In this way, gravity transforms from a vague notion into a precise tool, one that allows you to read the structure of the cosmos through patterns that can be measured and tested. For more than 2 centuries, This picture held with extraordinary success, shaping not only physics but the broader way people imagined the universe. Space became a stage in which objects moved under the influence of forces. Time flowed uniformly for everything, and the future could be determined from the present through calculation. The elegance of this framework lay in its clarity, because once the laws were known, everything else followed from them in a way that felt almost inevitable. Yet within that success, there remained a quiet limitation that did not immediately undermine the theory, but hinted that something deeper might still be missing. The rule described how objects influence one another, but it did not explain how that influence is carried across space or what mechanism allows one mass to affect another without any visible connection. The concept of force provided a way to calculate outcome, but it did not fully resolve the underlying question of what gravity is in its essence. That tension did not prevent the theory from working, and for a long time, it was not enough to challenge its authority, because the agreement between prediction and observation was too strong to ignore. Still, the absence of a deeper explanation remained in the background, not as an obvious flaw, but as an unanswered question waiting for a different way of thinking to bring it into focus. For a long time, Newton's picture held the universe together with such precision that it felt less like a model and more like reality itself. Yet the deeper you look, the more you begin to notice that it leaves certain questions untouched, not because they are unimportant, but because they require a different way of thinking altogether. The idea that objects pull on each other across empty space works remarkably well when you calculate motion, but it does not tell you what that pull actually is, nor how it moves from one place to another. And it is precisely in that gap that a new perspective begins to emerge. Einstein approached the problem from a direction that did not attempt to refine the existing picture, but to reconsider its foundation, starting with a simple observation that carries an unexpected weight. If you cannot distinguish through any local experiment whether you are being pulled by gravity or accelerated in empty space, then the two situations must be deeply connected, not just similar, but fundamentally equivalent in a way that cannot be ignored. This idea, known as the equivalence principle, does not immediately explain gravity, but it shifts the ground beneath the question, suggesting that what you experience as a force might instead be a reflection of something more geometric. To see where this leads, you have to let go of the assumption that space and time are fixed and passive, serving only as a stage where events unfold. Instead, imagine that they form a single structure, something woven together so completely that separating them becomes impossible, and that this structure is not rigid, but capable of bending, stretching, and responding to the presence of mass and energy. In this picture, objects do not move because they are pulled by forces in the usual sense, but because they follow the natural paths available to them within a geometry that has already been shaped by everything around them. The familiar analogy of a stretched surface with a heavy object placed upon it can give you a hint of this idea, showing how a smaller object might roll toward the larger one, not because it is being pulled directly, but because the surface itself has changed shape. Yet even this analogy is limited, because it relies on gravity to explain gravity, using a downward pull to create the very curvature it is meant to represent. The real situation is more abstract and more profound, involving the curvature of space-time itself, not something embedded within a higher dimension, but the structure in which all motion occurs. Once you begin to think in these terms, the concept of falling takes on a different meaning. An object in free fall is not being dragged downward by an external force, but is instead moving along a path that requires no effort. A path determined by the geometry of space-time. These paths, known as geodesics, represent the closest thing to straight lines in a curved environment. And what appears to you as acceleration is, from this perspective, simply the natural unfolding of motion in a space that is no longer flat. This shift in viewpoint resolves the tension that remained in Newton's description, because it removes the need for an invisible influence acting across empty space and replaces it with a local interaction between matter and geometry. Mass and energy tell space-time how to curve, and that curvature tells objects how to move, creating a relationship that is both precise and self-consistent. The motion of planets, the fall of objects, and the behavior of light can all be understood within this single framework, not as separate effects, but as different expressions of the same underlying structure. What makes this idea so striking is not only that it redefines gravity, but that it redefines what you mean by space and time themselves. They are no longer passive containers, but active participants in the dynamics of the universe, capable of changing in response to what they contain. This means that the geometry of space-time is not fixed, but evolves, carrying information about the distribution of matter and energy in a way that can be described mathematically with extraordinary precision. The consequences of this perspective extend far beyond the situations that first inspired it, reaching into phenomena that Newton's theory could not fully account for, such as the precise motion of Mercury or the bending of light near massive objects. Yet the most important change is conceptual rather than practical, because it transforms gravity from a force into a manifestation of geometry, replacing the idea of action at a distance with a description that depends entirely on the local structure of space-time. Nothing about the observable motion of objects needs to change for this new picture to hold. And in many everyday situations, it reproduces the same results that Newton's theory provides. The difference lies in how those results are understood, in the realization that what once appeared as a force acting within space is more accurately described as the behavior of objects within a space that is itself dynamic and curved. Once you begin to accept that gravity is not a force in the usual sense, but a feature of how space-time is shaped, something interesting happens to all the familiar experiences you thought you understood, because they do not disappear or change their outward behavior. Yet their meaning shifts in a way that quietly rewrites the story behind them. The act of falling, which once seemed like the most direct evidence of a pulling force, starts to look less like something being imposed on an object and more like something the object is doing naturally, as if it were simply following the only path available to it. To make sense of this, you have to adjust how you think about motion itself. In a flat, ordinary space, the natural path of an object moving without interference is a straight line, something that requires no additional explanation. In a curved space-time, that idea still exists, but the straight line is no longer what your intuition expects, because curvature changes what it means for a path to be straight. These paths, called geodesics, represent motion that is free of any external influence, even though, from your perspective, the object may appear to accelerate or curve. This is where the concept of free fall becomes essential, because it represents the closest thing to true. Unforced motion in a gravitational environment. When an object is in free fall, it is not being pushed or pulled in the conventional sense, but is instead moving along a geodesic determined by the curvature of space-time around it. The acceleration you observe is not the result of a force acting on the object, but the result of the geometry through which it moves. What makes this idea particularly striking is that it reverses your everyday interpretation of what it means to be at rest. Standing still on the surface of the earth feels like a state of inactivity. Yet in this framework, it is anything but natural, because your body is being prevented from following its geodesic path. The ground beneath you exerts a force upward, interrupting the motion you would otherwise take. And that interruption is what you experience as weight. The sensation that feels like gravity pressing down on you is, in fact, the result of the ground pushing up. This becomes clearer when you consider what happens in free fall, where that upward push disappears. In that state, your body no longer feels its weight, even though the gravitational influence has not been removed. The absence of resistance allows motion to proceed without obstruction. And in that unobstructed motion, the sensation of gravity vanishes from your experience. This is why astronauts in orbit appear weightless, not because they have escaped gravity, but because they are continuously following geodesic paths around the Earth. The motion of orbiting bodies provides one of the most compelling illustrations of this idea. Because what appears to be a delicate balance between forward motion and gravitational pull can instead be understood as a single, uninterrupted trajectory through curved space-time. The Earth itself is not being held in place by a constant struggle between opposing forces, but is moving along a path shaped by the presence of the sun. A path that requires no additional input once it has begun. The equivalence principle ties these ideas together by stating that the effects of gravity are locally indistinguishable from the effects of acceleration, a claim that at first seems abstract but becomes concrete when you imagine being inside a closed environment with no external reference. If you feel a force pressing you against the floor, you cannot tell whether you are standing on the surface of a planet or accelerating through empty space, because the experience is the same. This equivalence suggests that gravity is not a separate kind of interaction, but a manifestation of how motion is experienced within a curved space-time. What emerges from this perspective is a redefinition of what it means to feel gravity, because the sensation you associate with it does not arise from being pulled, but from being prevented from moving freely. The ground, the chair, any surface that supports you is constantly interfering with the path you would naturally follow, and that interference creates the pressure you interpret as weight. In contrast, the absence of that interference reveals a state in which motion proceeds without resistance. And in that state, gravity becomes invisible to direct experience. The familiar distinction between being at rest and being in motion begins to blur under this interpretation, because what feels like rest involves continuous interaction, while what feels like motion can represent a state of complete freedom from external influence. This inversion does not change what you see, but it changes how you understand it, replacing the idea of forces acting on objects with the idea of objects moving within a geometry that guides their paths, without the need for direct intervention. Once you accept that gravity is not a force, but a manifestation of curved space-time, the consequences begin to extend far beyond motion alone, reaching into aspects of reality that feel much less negotiable, especially your sense of time and the behavior of light, both of which seem so fundamental that it is difficult to imagine them being altered by anything at all. Yet this is precisely where the new picture reveals its full depth, because curvature does not merely guide the paths of objects. It reshapes the very structure through which events unfold. Time, which you experience as a steady and uniform flow. turns out not to be universal in the way you might expect, because in a curved space-time, the rate at which time passes depends on the gravitational environment closer to a massive object. Where space-time is more strongly curved, time flows more slowly compared to regions farther away, creating a difference that is not just theoretical, but measurable. This means that two clocks placed at different gravitational potentials will not agree with each other, even if they are perfectly constructed and synchronized at the start, because the structure of space-time itself causes their rates to diverge. What makes this idea particularly unsettling is that it does not rely on extreme or exotic conditions to become relevant, because even here on Earth, the difference can be detected with sufficiently precise instruments. Clocks placed at higher altitudes, where the influence of Earth's gravity is slightly weaker, run faster than those at lower altitudes. And although the effect is small, it accumulates over time in a way that cannot be ignored in systems that depend on precision. The operation of global positioning systems, for example, requires constant adjustments to account for these differences, because without them, the calculated positions would drift, not due to mechanical error, but due to the varying flow of time itself. Light, which you might expect to be unaffected by gravity because it has no mass, is also drawn into this picture, not by being pulled in the traditional sense, but by following the curved geometry of space-time. When light passes near a massive object, its path bends, not because a force acts upon it, but because the space through which it travels is no longer flat. This bending can be observed in the way distant stars appear slightly displaced when their light passes near the sun, an effect first confirmed during a solar eclipse, providing one of the earliest and most striking pieces of evidence for Einstein's theory. The bending of light does not stop at small deflections, because on larger scales, it leads to phenomena that reshape how the universe is observed. Massive galaxies and clusters can act as gravitational lenses, distorting and magnifying the light from objects behind them, creating arcs, multiple image, and patterns that reveal both the presence of visible matter and the influence of matter that cannot be seen directly. Through these distortions, astronomers are able to map the distribution of mass across vast regions of space, uncovering structures that would otherwise remain hidden. These effects are not isolated curiosities, but interconnected consequences of a single underlying principle, one that ties together the flow of time, the path of light, and the motion of matter within a unified description. Each observation reinforces the same conclusion, that space-time is not a passive stage but an active participant, shaping and being shaped by the contents of the universe in a way that can be measured with increasing precision. What gives this framework its strength is not only its conceptual elegance, but the consistency with which its predictions align with observation. From the earliest measurements of light deflection to the modern operation of satellite systems, the influence of curved space-time appears not as a rare or exceptional effect, but as a fundamental feature of reality that reveals itself whenever measurements become precise enough to detect it. As these confirmations accumulate, the shift in perspective becomes harder to ignore, because the idea that gravity acts as a force within space gives way to a description in which space and time themselves carry the imprint of mass and energy. The world you experience does not contradict this picture, but it no longer fully explains it either, leaving behind a sense that what once seemed stable and absolute is part of a deeper structure that continues to unfold as your ability to observe improves. As the curvature of space-time grows stronger, The gentle distortions that shape orbits and bend light begin to deepen into something far more dramatic, revealing regimes where the familiar patterns of motion give way to behavior that feels almost detached from everyday intuition, not because the underlying laws have changed, but because they are being pushed to their limits. It is in these extreme conditions that the full implications of Einstein's description come into view. And nowhere is that more evident than in the existence of black holes, objects so dense that the curvature they create alters not only the paths of matter and light, but the very structure of what can be observed or communicated. A black hole forms when a sufficient amount of mass is compressed into a region small enough that space-time curves inward without relief, creating a boundary known as the event horizon, beyond which no signal can return. This boundary is not a physical surface in the ordinary sense, but a limit defined by geometry, marking the point where all possible paths lead further inward rather than outward. An object crossing this threshold does not encounter a wall or a sudden force, but finds itself in a region where the future itself is directed toward the center, making escape not merely difficult, but impossible within the structure of space-time. From a distance, the behavior of objects approaching a black hole takes on an unusual appearance, because the flow of time near the horizon slows relative to an observer far away, causing motion to seem stretched and delayed. Signals emitted from near the boundary arrive increasingly redshifted and spaced apart, creating the impression that the object never quite crosses the horizon, even though, from its own perspective, the passage occurs within a finite interval. This difference in description is not a contradiction, but a reflection of how time itself is shaped by gravity, allowing two consistent yet distinct accounts of the same event. Deeper within, the curvature intensifies, leading toward a region described as a singularity, where the known laws of physics reach a point beyond which they no longer provide a complete description. This is not simply a place of high density, but a limit in the theory itself, indicating that the framework used to describe space-time breaks down under such extreme conditions. Whether singularities exist as physical entities or signal the need for a more fundamental theory remains an open question, one that connects directly to the unresolved relationship between gravity and quantum mechanics. The environment near a black hole also reveals subtler effects that arise from motion and rotation. When a massive object spins, it does not merely occupy space-time. It drags it along, twisting the surrounding geometry in a phenomenon known as frame dragging. This effect becomes especially pronounced near rotating black holes, where space-time itself is pulled into motion, influencing the trajectories of nearby matter and altering the region in which stable motion is possible. In such environments, the distinction between space and motion becomes increasingly blurred, as the geometry itself participates in the dynamics. Perhaps the most unexpected development in the study of black holes comes from the intersection of quantum theory and curved space-time, leading to the prediction that black holes are not entirely black, but emit radiation over time. This process, known as Hawking radiation, arises from quantum effects near the event horizon, where fluctuations allow energy to escape in a way that slowly reduces the mass of the black hole. Although this radiation is extremely weak for large black holes, its existence carries profound implications, suggesting that black holes can evolve and eventually evaporate, challenging the idea that they are permanent features of the universe. This leads to deeper questions about information, because if a black hole can evaporate, what happens to the information carried by the matter that fell into it? The apparent loss of information conflicts with the principles of quantum mechanics, creating a tension that has not yet been fully resolved, and pointing toward the need for a theory that unifies these frameworks in a consistent way. The study of black holes thus becomes more than an exploration of extreme objects. It becomes a testing ground for the limits of current understanding. What emerges from these considerations is a picture of gravity that is no longer confined to gentle curves and predictable motion, but extends into regimes where space-time itself behaves in ways that challenge the boundaries of theory. Black holes are not anomalies in the sense of being exceptions to the rules, but rather expressions of those rules under conditions where their consequences become unavoidable, revealing both the power and the incompleteness of the framework used to describe them. When space-time is allowed to bend, it is almost inevitable that it can also move. And once that possibility is taken seriously, gravity is no longer limited to shaping static structures like orbits or black holes, but becomes something dynamic, capable of carrying disturbances across the universe itself. These disturbances, known as gravitational waves, arise when massive objects accelerate in asymmetric ways, such as when two black holes spiral toward each other, losing energy not through friction or radiation in the usual sense, but through the emission of ripples in the fabric of space-time. What travels outward from such events is not matter or light, but a change in distance itself, a stretching and compressing that passes through space without needing a medium. For a long time, these waves remained a prediction rather than an observation, because their effects are extraordinarily subtle, altering lengths by amounts so small that they resist detection even with the most sensitive instrument. Yet persistence in measurement eventually led to their direct observation, confirming that space-time is not only curved but capable of vibration, and opening a new way of studying the universe that does not rely on light. Instead of observing distant events through electromagnetic signals, it becomes possible to listen to the cosmos through the distortions of space-time itself, capturing information from regions that might otherwise remain hidden. As this picture expands, gravity reveals another layer of mystery, not through what is seen, but through what is missing. The motion of stars within galaxies, when analyzed carefully, does not match what would be expected from the visible matter alone, because stars at the outer edges move faster than they should if only the luminous mass were present. This discrepancy suggests the existence of additional matter that does not emit or absorb light, a form of mass that interacts gravitationally but remains otherwise invisible. This unseen component, referred to as dark matter, appears to dominate the mass of galaxies and clusters, shaping their structure and evolution while eluding direct detection. The presence of dark matter introduces a subtle tension into the narrative because it extends the reach of gravitational theory without fully revealing the nature of what is being described. The equations continue to work. The predictions align with observation. Yet, a significant portion of the universe is accounted for by something that has not been directly observed in the traditional sense. This situation mirrors, in a different way, the earlier reliance on the concept of force, where calculation succeeds even as the underlying mechanism remains uncertain. If dark matter complicates the story by adding unseen mass, dark energy reshapes it at an even more fundamental level by altering the large-scale behavior of the universe itself. Observations of distant galaxies reveal that the expansion of the universe is not slowing down under the influence of gravity, as might have been expected, but accelerating, driven by a component that acts in opposition to gravitational attraction. This effect is attributed to dark energy, a form of energy associated with the structure of space-time that becomes significant over vast distances, influencing the evolution of the cosmos in a way that is still not fully understood. The expansion of the universe, once established as a central feature of cosmology, changes the way you think about space itself, because it is not objects moving through a static background, but space stretching, carrying galaxies apart as it grows. This distinction matters because it means that the large-scale dynamics of the universe are governed not only by the distribution of matter, but by the properties of space-time as a whole. The idea of a beginning, often associated with the Big Bang, emerges not as an explosion within space, but as a state in which space-time itself was compressed and has been expanding ever since. As these elements come together, the universe begins to look less like a collection of isolated systems and more like a connected structure shaped by gravity across every scale. From the merging of black holes to the motion of galaxies and the evolution of the cosmos as a whole. The same underlying framework that describes the fall of an object near you extends outward to describe the behavior of regions so distant that their light has taken billions of years to reach you, linking the local and the cosmic through a continuous set of principles. Yet within this expanding picture lies a growing awareness of how much remains unknown, because the components that dominate the universe, dark matter and dark energy, are understood primarily through their gravitational effects rather than through direct observation. The theory continues to describe what happens with remarkable accuracy, but the nature of what is causing those effects remains open, suggesting that the current understanding, while powerful, may still be incomplete in ways that only become visible when the scale of inquiry is extended far enough. By the time you arrive here, the picture of gravity has already expanded far beyond anything that could have been anticipated from the simple act of watching an object fall. Yet even this expanded view carries within it a quiet incompleteness, a sense that the framework, for all its success, does not fully close the circle. General relativity describes the large-scale structure of space-time with extraordinary precision, capturing the motion of planets, the formation of black holes, and the evolution of the universe itself. But when you turn your attention to the smallest scales, where quantum effects dominate, the coherence of this description begins to unravel. The difficulty does not arise from a lack of effort or ingenuity, but from a fundamental mismatch between the two most successful theories in physics. Quantum mechanics describes reality in terms of probabilities, fluctuation, and discrete interactions, while general relativity treats space-time as a smooth, continuous geometry. Each works within its domain with remarkable accuracy. Yet when conditions demand that both be applied at once, such as near the singularity of a black hole or at the earliest moments of the universe, their assumptions no longer align, and the result is not a unified picture, but a tension that has yet to be resolved. This unresolved tension has led to the search for a theory of quantum gravity, an attempt to describe space-time itself in a way that incorporates quantum principles without losing the geometric insight that makes relativity so powerful. Various approaches have been proposed, from string theory, which suggests that fundamental particles are manifestations of tiny vibrating structures, to loop quantum gravity, which attempts to describe space-time as composed of discrete units rather than a continuous fabric. Each approach offers partial insight, yet none has achieved the level of experimental confirmation required to establish it as a complete theory. What makes this situation particularly intriguing is that gravity, which once seemed like the most straightforward of phenomena, now occupies a central role in the deepest open questions about the nature of reality. The same concept that explains the fall of an object and the motion of galaxies also points toward the limits of current understanding, suggesting that the path to a more complete theory must pass through an even deeper rethinking of space, time, and interaction. At the same time, gravity connects scales in a way that few other concepts do, linking the smallest measurable effects to the largest structures in the universe. The behavior of subatomic particles, the formation of stars, the dynamics of galaxies, and the expansion of the cosmos are all influenced, directly or indirectly, by gravitational interactions, creating a continuity that runs through every level of physical description. This continuity does not imply simplicity, but it does suggest that a unified understanding, if achieved, would carry implications across an extraordinary range of phenomena. There is also one that extends beyond technical questions and touches on how you understand your place in the universe. The recognition that the same principles govern both the motion of your body and the structure of the cosmos creates a connection that is not merely poetic, but grounded in the actual behavior of nature. You are not separate from the system you are trying to understand, but part of it, subject to the same laws that shape everything from falling objects to expanding galaxies. Yet the incompleteness remains, not as a failure, but as an invitation, because each unanswered question points toward the possibility of a deeper level of understanding that has not yet been reached. The search for quantum gravity is not simply about resolving a technical inconsistency, but about discovering whether the concepts of space and time themselves need to be redefined once again, just as they were in the transition from Newton to Einstein. What began as a question about why things fall has led to a framework that describes the evolution of the universe and to a set of questions that reach beyond current theory, forming a chain of ideas that continues to extend outward. The story does not end with a final answer, because no such answer has yet been found, but with a recognition that the process of understanding is ongoing, shaped by observation, guided by theory, and continually revised as new insights emerge.